Let's now consider delta hedging in the Black-Scholes model. Suppose that we have a derivative x on some underlying assets, S1 up to Sn. This could be a derivative on a single underlying asset, like a vanilla call or put. It could also be on multiple assets, for example a rainbow option, which is an option on the maximum or minimum of a collection of underlying assets, or a basket option, which is an option on the sum of some underlying assets. And suppose that we must hedge this derivative. Now, under the risk-neutral measure Q, the dynamics of the discounted asset prices are given as follows, where sigma n is the nth row of the volatility matrix, and W is a multidimensional Brownian motion. By the martingale representation theorem, there is a replicating portfolio for every f capital T measurable pair of xt. However, the martingale representation theorem does not tell us how to find such a replicating portfolio. Now, we know by risk-neutral valuation that the price of such a derivative is given as follows, where we've assumed here that the riskless rate is constant. If it wasn't, we'd have to represent this as an integral and take the integral inside the expectation. Now suppose that we can evaluate this expectation explicitly as a function of time and the asset prices. We've already seen how to do this for European calls and puts, and we can also do this for digital options, barrier options, rainbow options, etc., some of which we'll see later in this course. Now suppose that theta is a replicating portfolio for the payoff of the derivative x capital T. In that case, the functional form VTST, i.e. this form here, is equal to the value of the portfolio by the law of one price. And in that case, we've seen that the dynamics of the discounted portfolio are given as follows. Now, when we derived the multidimensional Black-Scholes PDE, we also saw that the dynamics of the discounted portfolio are given as follows. Equating these two expressions for dV bar, we obtain the following. And as you can see, sigma n, S bar n, and WQ are common to both sides. However, the left side has a theta nt and the right hand side has a partial dV by dsn, and that suggests theta nt is equal to partial dV by dsn. And this partial derivative is known as the delta of the option with respect to the nth asset. Thus, in the case where we can get an explicit expression for the price of the derivative in terms of time and the underlying asset prices, we know how to construct a replicating portfolio. At each time t, you must simply hold delta n many assets Sn and adjust the bank account component to make the portfolio self-financing with initial value equal to x0, which is defined to be this conditional expectation here. Now, the Black-Scholes model, with its constant volatility and constant interest rate, is often given bad press. It assumes constant volatility, which is clearly not the case if you look at the data. It also implies that returns are normally distributed, which is also contradicted by empirical data. Nevertheless, when used to hedge, it often works surprisingly well. Here, we'll hedge a 3-month European call option on the S&P 500 index at a bad time. Here we've read in the data, which is 3 months of daily data for the S&P 500 index, starting in January 2009. If we plot what this looks like, we obtain the following. Observe that the S&P 500 index starts at about 930 and ends just over 800. I said it's a bad time, and that's because the volatility index, also known as the fear index colloquially, looks like this, and we are here. We've just had a massive spike in volatility, and volatility is obviously not constant. Nevertheless, we're going to take this volatility here, which is about 39%, and use it to hedge an option starting at this particular time. So if we define the Black-Scholes call formula and the delta, and then construct a hedging portfolio, with a strike of 900, we obtain the following. Now, the S&P 500 index ended at around 800, so a strike of 900 means that the option expired out of the money. And as you can see, the value of the hedge portfolio is slightly above zero, whereas of course the value of the actual option is zero. And so the terminal value of the call option and the hedge portfolio are very, very close. I've shown here the BlackScholes price in red and also the value of the hedge portfolio in blue. I don't actually know that the value of the call option is the BlackScholes price because we don't know what the true dynamics of the asset are. However, we do know that at the terminal time, the BlackScholes model is correct, because at the terminal time, the value of the option is just equal to the payoff. And hence, I'm really interested in what happens over here at the terminal time. If I do this with a strike of 700, so that the option expires in the money, we also see that the terminal value of the portfolio and the payoff are almost the same. This works even if we have a strike which is much lower, in other words, an option that expires much more deeply in the money, say 400. And if it expires much more out of the money, it turns out that our hedge portfolio is slightly positive, whereas the option is worthless, as you can see. One of the exercises will explain why the BlackScholes model seems so unrealistically effective at hedging.